Alright, 8.2, day number 1, differential equations. Today's goals are going to be differential equations in slope fields. So let's read this definition of differential equations. An equation that involves a derivative is called a differential equation. The order of a differential equation is the order of the highest derivative involved in the equation. So this one, for example, would it be a first order differential equation? Okay, because it's the first derivative. So find all functions y that satisfy this. Okay, so the first thing I would do is I'd multiply both sides by dx. Okay, so that'd be secant squared x plus 2x plus 5 and dx. So I'd have dy equals this times dx. Now I would integrate both sides because I want to find a function whose derivative is that. Okay? So if I integrate both sides, on the left I would get y. Right? The integral of 1 dy would be y plus some constant, but I don't really care. I'm not going to leave that on that side. I'm going to bring it over to the other side in a minute anyways. And on the other side I would get tangent x plus x squared plus 5x plus c. So I could have written my equation as y plus c1 equals, tangent x plus x squared plus 5x plus c2 plus c2. And then I would have just subtracted c1 from both sides, and then I get this c. So I just keep that constant on that one side by itself and save myself a little bit of work. Alright, let's move on to another example. If the general solution to a first order differential equation is continuous, the only additional information needed is the value the function takes at a single point called an initial condition. What the initial condition will do is it'll help you to solve for what that c value is. A differential equation with an initial condition is called an initial value problem. It has a unique solution called the particular solution to that equation. So let's do the same thing on this, knowing that the initial condition here is 1, 0. Alright, so multiply both sides by dx. I get e to the x minus 6x squared dx. I integrate both sides. So I get y equals e to the x minus 2x cubed plus c. Now enter initial condition. So if y equals 0 when x equals 1, that would be 1 cubed. We can now solve for c. So algebraically, to solve for c, I would subtract e and add 2. So negative e plus 2 equals c. So the particular solution to this differential equation with initial condition 1, 0 would be y equals everything we see here plus our initial condition. So e to the x, that's a minus 2x cubed minus e plus 2. That would be, if you took the derivative of that, you would get our original. Okay, what about this one though? Well, we can't find the solution to that due to the fact that both x and y exist in the same function. There are other methods in order to find the differential equation, the particular solution to that. But one way that we do it is we use slope fields. So we draw small pieces of tangent lines for each point in the coordinate plane. This is called linearization. This approximates the solution curve that passes through that point. Repeat that process as many points to yield a picture of the solution curves. So let's construct a slope field for a moment for functions whose differential equation cannot be solved algebraically. So my differential equation in this case is x plus y. So what I'm going to do is I'm just going to plot a bunch of points, right? Because this differential equation is dependent on both x and y, I'm going to figure out what dy dx is based on this right here. So this will give us a bunch of slopes. So if x is 0 and y is 0, when I add those two together, x plus y will still equal 0. So our slope at 0, 0 will be 0. Okay, when x is 1 and y is 1, x plus y is 2. So our slope at 1, 1 is 2. Okay, when x is 2 and y is 2, our slope is 4. So our slope is 4. Now these are all, obviously you can tell just, by just a little bit of practice, these are estimations, right? They're not perfectly a perfect slope of 4 or 2. 0 I better be okay with, but 4 or 2 definitely. They're just approximations, okay? So at 3, 3 our slope is 6. And at 4, 4, of course, our slope would be 8. That's not going to show up on this graph, though. Now, what's cool is that I think 2 plus 2 is the same as 1 plus 3, and 3 plus 1. Okay, 1 plus 1 is the same as 2 plus 0. Okay, or 0 plus 2, or negative 1 plus 3, or 3 plus negative 1. So these slopes, they show up on a number of bases here. All right, so what about in between? Well, what about x is 2 and y is 1? Well, if I add those two together, I get 3. So in here, I'm getting 3's. So you can see this slope field starting to take shape. I'm going to just put another grouping of these here. So at 3, 2, I would have a slope of 5. This would be 5 as well. All right, and then let's just fill in a few of the rest using black here. Negative 1 and 1 would be 0, and 0, and 0, and 0, and 0, and 0. And then at each of these values, we would get a slope of 1, 1, 1, 1, 1, and 1. I'm going to fill in the rest of the slope field on the bottom left half of this graph. You could do the same. Okay, so you can see I get a negative 1 all the way along here. I get a 0 here. And I get a positive 1, then a positive 2, then a positive 3, then a positive 4, then a positive 5, then a positive 6. Over here I get a negative 1. These are all negative 2, negative 3, negative 4, and looks like negative, negative 1, 2, 3, 4, 5, and 6. Okay, so let's just plot a point. Let's say our initial condition was this point right here, 0, 1. Okay, what would the graph probably look like? Well, it would probably look something like this. Okay, the slopes would kind of be shaped by the slopes around it and probably end up coming to an asymptote right there. All right, what if our initial condition was right here? Well, the slopes around it would kind of shape it. Oops. Okay, kind of like that. And it would approach this asymptote that way. Now, we don't have an equation for these functions, but this will allow us to at least see the behavior. So slope fields are helpful if you're not able to come up with that particular solution. Here's a few features that you're going to want to be aware of. This will help you to determine, maybe if you've got multiple choice, you've got a differential equation, you want to match it to a slope field. These are really good tips right here. All right, one of the following slope fields in this one is sine of x plus y, and the other, for the differential equation, sine of x minus y. So one of them represents sine of x plus y as its slope, and the other represents sine of x minus y as its slope. Okay, so the two things that I look at right now are about right here. That looks like a slope of negative 1 to me. And that slope of negative 1 has absolutely no dependence on y because y is 0 right there. So that tells me that the derivative here, right, dy dx, dy dx equals -1 there, okay, and y is 0. So that's the sine, so y has no effect on it, so the sine of x equals -1 at that point, right? I know that the sine of, what would it be, negative pi over 2. I know that the sine of negative pi over 2 equals -1. So I'm gonna just go on a limb here and say that at this point x equals negative pi over 2. Okay, with the same thought in mind, I'm gonna look over here and I see a dy dx equal to +1 there, or approximately there. So, all right, and again, this would be sine of x equal to +1. That tells me that the x value there should be pi over 2. Okay, so then let's just project, and let's say that this is right here, negative pi over 2. That would make this negative pi. And the slope right here, right, we could say that this point right here would be the point negative pi comma pi over 2. If I added those two together, if I said negative pi plus pi over 2, right, if I just added them together, if I added the x and the y, negative pi plus pi over 2, that would just give me, or yield me again, negative pi. And what is the slope at that point? The slope is still -1. So right here, this tells me that I believe this function would be, or this graph would be the slope field, dy dx equals sine of x plus y. Let's just confirm by looking at the other one. That would be the point x equals pi over 2. So projecting out a little bit further, we're going to see the same slope. This point right here, which has a slope of +1, would be, it looks like, what would that be, pi comma pi over 2. So the slope, if I want the slope to equal 1, dy dx would equal, let's take pi minus pi over 2. And of course that would get this the sine of pi over 2, which is 1. Therefore, this graph would be the graph of the slope function, or the slope field of sine of x minus y. All right, let's look at another example. The slope field for the certain differential equation is shown above. Which of the following could be a specific solution to the equation? Well, I could just take an initial condition. Let's take this point right here. That graph should start to look, right, it's going to just kind of follow some of the slopes along the way. That does not look like x squared. That does not look like e to the x. Cosine x, no. I would say no, because at 0, 0 it has a slope of 1. Therefore, that's out. And e to the negative x, that graph looks like that, right, with respect to the x and y axis, so that would have to be the natural log of x. The slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? To me, it kind of looks like there's some kind of almost asymptotic here. You can see these look almost like asymptotes, but they're not, because none of these functions here have asymptotes on both symmetric sides of the x or the y-axis. So I'm going to take sine out and cosine out, because they should start to, sine and cosine would begin to cycle. X squared is out, because it would behave this way on the left side. Natural log of x is out, because it doesn't exist to the left of 0. So I guess that only leaves this. And that makes sense, right? Because a cubic function looks like this, so its slopes would start to behave that way. Alright, so use slope analysis to match each of the following differential equations with one of the slope fields A through D. Do not use your calculator, right? Make this something that you learn along the way. So why don't you give it a try, and I'll give you some answers in a moment. Okay, so the easiest one to identify probably right away would be number 10, okay? The slope is just whatever the x value is. So where I look immediately would be at x equals 0. See how when x equals 0, the slope is 0. When x equals 1, the slope is 1. When x equals 2, the slope is 2, etc. and down the line. So B would be number 10, right? We would match those two. So that one's out. I've used it. The next one I would see almost immediately is the graph of the derivative of sine x, or the slope field of sine x, is going to look similar to sine. It's actually going to look a little bit more cosine-ish, because the integral of sine is negative cosine. So I would just be able to very quickly match those two, which would be C, right? So this would be number 7. All right, so it brings me to this, right? Where would x minus y equal 0? Well, it'd be when those two are equal. So anywhere 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, etc. That's where I would be seeing a slope of 0. So here at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, I'm seeing that. And so therefore, that leaves us here. Now let's make a little, instead of just saying, oh, it's process of elimination, let's look at this a bit. Where would the slope here be 0? Well, it would be 0 everywhere that y equals 2. Well, look here, y equals 2, y equals 2, 2, 2, 2, all the way down the line. That should be a good indication right there that that would be number 9. All right, that's slope fields. And we'll move on a little bit more with some integration problems in the lessons to come.